Can you see the screen now?
Okay. Yep.
Okay. Yeah. Let me continue. So the first proposition is that SL2Z acts on the upper half complex plane, and the proof is really straightforward. We just need to use the definition of action. First, we need to show that for any gamma in this group, the gamma maps this point Z. Still, the image of Z is still on the upper half complex plane. So for this, we just need to verify that the imaginary part of gamma of Z is still positive, and this can be easily done because we have such kind of relation. The imaginary part of gamma of Z differs from the imaginary part of Z only by a simple factor, which is 1 over C, the modulus of CZ plus D square. And the second part is we need to show that for the identity matrix, I x on Z does not change Z. So this is really easy. And as for the third part, we need to verify that for any two matrix, gamma and gamma prime, we must have gamma after multiplying gamma by gamma prime, the new matrix X on Z is the same with you act by gamma prime first, and then you act by gamma in the second place. This is the same, and this is easy to verify. So this group does act on the upper half complex plane. And now we can give a definition for modular function. Let K be an integer or meromorphic function f from the upper half complex plane to the set of complex values. We call f as a weakly modular function of weight k when f satisfies the following functional equation. That is, f of gamma of z equals to cz plus d to the kth power times f of z. And this must hold for any gamma in SL2z. So this functional equation is the key for meromorphic function to be modular. And the k here is called the weight of f. And recall that SL2z is generated by S and T. So in order to verify whether f is a modular function or not, we do not need to work with every matrix here. Instead, we just need to verify this functional relation with the matrix S and T. So this simplifies this definition. And thus we have, for any meromorphic function f, it is weakly modular of weight k if and only if f is periodic with period 1. That is, fz plus 1 equals to fz, and f negative 1 over z equals to z to the kth power times f of z. So this relation is because of the matrix T, and this relation is corresponding to the matrix S, because the action T over z is equals to z plus 1, and the action of S over z equals to negative 1 over z. And because the set is generated by these two matrices, so this relation reduces to these two simple relations. Okay. And we have we have no non-zero odd weight weakly modular functions. That is this proposition. If the weight k is odd, and f is a weakly modular function of weight k, then f must be 0. And therefore, we only need to consider even weight modular functions for SL2Z. The reason is also simple. You just need to consider the matrix negative I. And according to the definition, you must have f of gamma of z equals to negative 1 to the kth power times f of z, because negative I is equals to negative 1, 1, 0, 0. So here, in the original definition, it is zc plus d to the kth power, but because c is 0 and d is negative 1, so this is negative 1 to the kth power. And since k is odd, so this equals to negative f of z. And the left-hand side, it is still f of z. So comparing the left side and the right side, we conclude that f of z must be 0. Hence, For SL2Z, we only need to consider even weight. And roughly speaking, modular forms are weakly modular functions that are also holomorphic on the upper half plane and holomorphic at infinity. Because for weakly modular functions, we just require that f to be meromorphic. But later, when we define modular forms, we require the function f to be also holomorphic. So this is the difference. Now, let me give the definition for modular form. Let k be an integer of function f from the upper half complex plane to the set of complex values. We say f is a modular form of weight k on the 4 modular group. So the 4 modular group is just means the SL2Z. So we say f is a modular form on SL2Z if first f is holomorphic on the upper half complex plane, and second, f is weakly modular of weight k. This means that faz plus b over cz plus d equals to cz plus d to the kth power times of z. This is the original definition of weakly modular functions. And third, f must be holomorphic at infinity. So when f satisfies these 3 requirements, we say f is a modular form of weight k. And the set of modular forms of weight k is denoted as mk of SL2Z, or simply we write as m sub k. When this set is fixed, we just say it is mk. So the key difference between modular form and modular functions is that we require it to be holomorphic on H and holomorphic at infinity. This is the key difference. And we have some well-known facts. First, the space of modular forms is a vector space. And second, if F is a modular form of weight K and G is a modular form of weight L, then the product of F and G is a modular form of weight K plus L. And this fact is also easy to verify when using the definition. So I will omit the details. And there are some simple examples. First, the zero function, of course, it is a modular form for any weight because this is very easy to see. And when C is a non-zero constant, then the constant function C is a modular form of weight 0. And then let's give some non-trivial examples of modular forms. Let K be an even integer greater than 2. We define the Eisenstein series of weight K by the following summation. So the summation is, the summand is 1 over mz plus n to the kth power. And the sigma prime, the prime summation here means the summation range is over all non-zero vectors m and n. So this means m and n are cannot be simultaneously 0. This is a double summation, and one can verify the convergence of the summation. So this is called the weight K Eisenstein series, and it's denoted by GK of Z. We can prove that GK of Z is actually a weight K modular form on the 4 modular group. So for this, you just need to verify several points. First, you need to verify it is holomorphic on H and the infinity. And then you must show that GKZ plus 1 equals to Z to the kth power times GK of Z. And the second, you need to show GK minus 1 over Z equals to, this is just equals to GKZ. This means for this, you need to time Z to the kth power. You just need to verify these two functional equations. And the first one is very clear because when you change Z to Z plus 1, the sum will not change. And for the second one, it is also easy. Okay, this is a very classical example for modular forms. But this version, sometimes this version is not convenient for our use. So we can also find the Fourier series expansion for GK of Z. We recall the famous Riemann zeta function. The zeta function zeta of S is defined by the summation of 1 over n to the s power. Here for convergence, we need the real part of S to be greater than 1. Now we have the following proposition. Let Q we use Q to denote e to the 2 pi I z. Of course, we require the imaginary part of z is greater than 0. This is also means that z belongs to the upper half complex plane. And we use sigma sub m of n to denote the sum of the m's power of all the divisors of m. This is a very classical arithmetic function. And now with this notation, we can find the Fourier series expansion for GK of Z. That is for k being an even number greater than 2, GK of Z can be written as the constant term 2. The constant term is 2 times zeta of k plus 2 times of factor and then times power series in Q, and the nth coefficient is just sigma sub k minus 1 of n. So this is a very nice formula or not very nice expansion for GK of Z. And now in this expression we have the irrational number pi. So this is the irrational number, and the zeta of k we also want to know its value. Therefore, we sometimes want to simplify the expression of GK of Z. For this purpose, we need to know the value of the Riemann zeta functions, and this is also a very well-known result. For k greater than or equal to 1, the value of zeta of 2k is equals to the 2k's Bernoulli number times pi to the 2k's power times a rational number. Here, Bn is the nth Bernoulli number defined by the Taylor expansion of this function. So the Bn is defined by the Taylor expansion of this function. And by some calculations, by some simple calculations, we can find some initial values for the sequence Bn. For example, B0 equals to 1, B1 equals to negative 1 over 2, B2 equals to 1 over 6, and etc. So actually, we have some simple results such as B sub 2n plus 1 equals to 0 for n greater than or equal to 1. Okay, this is the Bernoulli numbers, and it appears in the value of zeta 2k. Now with this formula, we substitute this formula into the previous expansion. So now we know the value of this part, and after extracting the common factor from this part and this part, we can give the normalized Eisenstein series. So we will use more frequently the normalized Eisenstein series. That is, we divide GK of Z by its constant term that is by 2 times zeta of k. After dividing by 2 times zeta of k, then this Eisenstein series becomes a power series with only rational coefficients. And this is denoted by E sub k of Z. So this is called the normalized Eisenstein series, because now the leading term is 1. This corresponds to the term normalized. We call this is a normalized Eisenstein series. So you may wonder, why do we need k greater than or equals to? So for here we need a k greater than or equals to 1, but for the previous slides we need a k greater than or equal to 2. So what happens for when k equals to 1? When k equals to 2, what happens when for the function E2 of Z? Actually, E2 of Z is also meaningful. If we define it in this way, if we define the way2 Eisenstein series as 1 minus 24 times this power series. However, this is not modular, because when we when we justify the functional equations, we will see that E2 of z does not satisfy the second functional equation because E2 of -1 over z, for modular function, we must have this equals to z to the k minus times f of z. However, here, in other words, if you multiply by z to the negative k here, then this must be equal to fz. However, here, you differ from E2 of z by an extra part. So this means E2 of z is not modular. It is not a modular form. Nevertheless, though it is not a modular form, it still plays a very important role in the theory of modular forms. Okay, there are two fundamental facts here. The two Eisenstein series, E4z and E6 of z, they generate the algebra of all modular forms on SL2z. So what does this mean? This means that for any even positive integer k greater than or equal to 4, the space of weight k modular forms on SL2z is generated by monomials of the form E4 to the s power times E6 to the b's power. Here a and b are greater than or equal to 0, and 4a plus 6b equals to k. This means that the weight, because the weight of E4 is 4 and the weight of E6 is 6, so the weight of this product must be 4a plus 6b. And for this product to lie in this space, we must require 4a plus 6b equals to k. And this is why we have such kind of restriction. Okay, and we can also evaluate the dimension of such vector space. The dimension of the space MK is given by these two formulas. And then now we will turn to the subgroups of the four modular group, which is called the congruent subgroups. So now let's define three kinds of congruent subgroups for SL2Z. Let M be a positive integer, then we define the level n congruent subgroups gamma 0 n, gamma 1 n, and gamma n by these three sets. So gamma 0 n means all such kind of 2x2 matrix in SL2Z. The requirement is that the two Wang entry which is visible by that we need A and D to be congruent to 1 modular n, and C must be divisible by n. And for gamma n, we need A and D congruent to 1 modular n, and B and C congruent to 0 modular n. So these are three spatial subgroups of gamma of SL2Z. And it is straightforward to verify that they are indeed subgroups and they have such kind of inclusions. Gamma 0 n is the biggest, and gamma n is the smallest among these three groups. And in particular, when capital N equals to 1, then gamma 0, 1, gamma 1 of 1, or gamma 1, they are the same group. They all agree with SL2Z. And next, suppose gamma is a congruent subgroup of SL2Z, then a cusp of gamma is an equivalence class in Q union with capital union with the point of infinity under the action of gamma. So this means you can act this set by the matrix in gamma, and then you can get some equivalence classes. So a cusp means an equivalence class. And there is only one cusp when gamma equals to the 4 modular group. And usually we just select the point infinity to denote this equivalence class. Okay, I think I need to speed up. And when gamma is a positive integer, we can evaluate the index of the subgroups gamma 0 n in gamma 0 1. So gamma 0 1, as we just said, this is just SL2Z, and this is just SL2Z. So the index of gamma 0 n in the 4 modular group is equal to n times this kind of product, and the index of gamma 1 n in SL2Z is equal to this product. Here the product are taking over all prime divisors P of n. So now we can define the modular form on the congruent subgroups. Suppose that f of z is a meromorphic function on the upper half complex plane and k is an integer. Suppose that gamma is a congruent subgroup of level n, then fz is called a meromorphic modular form with weight k on gamma if the following two conditions hold. First, we still require the functional equation, which means f of gamma of z equals to fz times cz plus d to the kth power. And this must hold for all z in the upper half plane and all abcd in gamma. And in particular, in addition, for any gamma 0 in SL2Z, the action of f, so this action means the action fk gamma 0 means cz plus d to the negative k times f gamma of z. So this function has we require that it has a Fourier expansion of such kind of form, have such kind of form, which means it is meromorphic. And in particular, if k equals to 0, then fz is called as a modular function on gamma. So generally, it is called a meromorphic modular form. And in particular, when k equals to 0, you can also call it as a modular function. So the term here is a function, and here it is a form. This happens when the weight is 0. You can use another name. You can call it as a modular function. Okay, the second condition looks a bit strange. As you see, this condition, it looks a bit strange, but it just means that the function fz must be meromorphic at the cusps of gamma. Okay, when the second condition in the expansion, when the least power n gamma 0 is greater than or equal to 0, then we see that fz is holomorphic. And when the least power in Q is greater than 0, then we see that fz vanishes at this cusp, which means fz takes the value 0 at the cusp. Now we can define the holomorphic modular form. In the previous slides, we are defining the meromorphic modular form. Now we can define the holomorphic modular form. Suppose fz is an integer with meromorphic modular form on the congruent subgroup gamma, which was just defined in last slide. Now we say that fz is a holomorphic modular form if fz is holomorphic on the upper half complex plane and is also holomorphic at the cusps of gamma. And this means this condition must be satisfied. And if fz is we say fz is a cusp form. We say fz is a cusp form. It's a cusp form if the fz it vanishes at the cusp. So this corresponds to n gamma 0 is greater than 0. And we say fz is a weakly holomorphic modular form if its poles are all supported at the cusps of gamma. And we denote the vector space of holomorphic modular forms by mk gamma 1n, and we denote the space of cusp forms by sk gamma 1 of n. So, and for simplicity, we shall refer to a holomorphic modular form as a modular form. So by modular form, we mean the holomorphic modular form. Okay, so far we have go through some very basic facts in the theory of modular forms. And in most of the time, we will only deal with certain modular forms in mk gamma 1n. And actually, we usually deal with those forms with nice properties with respect to gamma 0 of n. And hence, we need one more definition. If chi is a dirichlet character modular n, then we say that a form fz in mk gamma 1n has Leibniz character chi, if fz satisfies this kind of functional equation. So comparing with the original definition, the only difference is here we have another factor chi of d. Yeah, this is the only difference. And the space of such modular forms is denoted by mk gamma 0 n gamma 0 n and chi. And of course, when the form is vanishes at all the cusples, then we denote it by sk gamma 1 of n or sk gamma 0 of n. In particular, when the character chi is trivial, then we denote we will just omit it. When the character chi is trivial, then we will just omit. We will just delete this and just simply denote as mk gamma 0 of n. Okay. The last page for this part, we need the decat eta function, which is denoted by eta of z. It is defined by this kind of infinite product. So again, here q equals to e to the 2 pi I z. So this is a functional in q and also functional in z. This is called the decat eta function. And this function has very nice properties. First, it does not vanish on the upper half plane. And second, it satisfies this kind of nice transformation formulas. First, eta of z plus 1 differs from eta of z only by the simple factor. And the eta of negative 1 over z differ from eta z only by this another factor. So these two functional equations means that eta 24 times z is actually a weight 1/2 holomorphic modular form. So in the previous definitions, we require the weight to be an integer, but here we honor the weight to be of any half integers. But since time is limited, we will not discuss half integer weight modular forms. Okay, maybe you find that this part is really boring because we are just reviewing some basic facts from the theory of modular forms. But this is necessary because we want to use modular forms to settle some problems in the theory of partitions. And now let's turn to the theory of partitions, which I think Wuhan has already delivered a lecture. So for this part, you will find something very similar to Wuhan's lecture. Okay, let us do some easy things because you have already known the partition function. So this part can be done more first. A partition of a positive integer n is a way of writing it as a sum of positive integers in non-increasing order. And we denote the number of partitions of n by p of n, and we agree that p of 0 equals to 1. For example, there are 5 partitions. There are 5 partitions of 4. There are 5 partitions of 4, and hence p of 4 equals to 5. And these are the 5 partitions of 4. And all enough found that the generating function for p of n equals to an infinite product, which is denoted by qq sub infinity. So here we are using the q series notation, which means aq sub infinity denotes the product, the infinite product. The first term is 1 minus a, the second term is 1 minus aq, and here 1 minus a to the aq square, and so on. And we can also define the finite product aq sub n by aq sub infinity divided by aq to the nth power q sub infinity. So in other words, this is the same with aqn means 1 minus a times 1 minus aq till 1 minus aq to the n minus 1's power. And this holds for all n being either a non-negative integer or the infinity. So for convergence, we need the modulus of q to be less than 1. This is for the sake of convergence. And Ramanujan discovered three beautiful congruences, which Wuhan has also mentioned, I think. First, P5n plus 4 is divisible by 5, P7n plus 5 is divisible by 7, and P11n plus 6 is a multiple of 11. And there are now many different approaches to prove these three congruencies. And one of the way to prove them is to find the generating function for the relevant subsequences. For example, Ramanujan, along this direction, Ramanujan found that the generating function for P5n plus 4 equals to 5 times another infinite product, and the generating function for P7n plus 5 is the linear combination of two different infinite products. And since all these series have integer coefficients, when you're making a power series expansion, all the coefficients are integers, and you have a 5 here. So this immediately, it means that P5n plus 4 is divisible by 5. And here, since you have 7 here and 49 here, they are all multiples of 7. So this immediately shows that P7n plus 5 is divisible by 7. So this is a very good way to prove the congruencies, and it actually give you more information than the congruence itself. And Ramanujan himself gave a sketch of proofs of the above identities. And G.H. Hardy, a very famous number theorist and mathematician, he makes the following comments. It would be difficult to find more beautiful formula than the Rogers-Ramanujan identities. So these two identities I will not mention here. But here, Ramanujan must take second place to Rogers. And so what we want to focus is the second part. And if I had to select one formula from all Ramanujan's work, I would agree with Major Wang, in selecting 2.7. So in other words, Hardy says that this formula is the most beautiful formula of Ramanujan. Yeah, this is Hardy's comment. And there are several proofs for these two identities. Some of them are truly elementary and only use some basic identities, such as the Euler's identity, which gives the Q expansion for QQ sub infinity. And another key identity is the Jacobi triple product identity, which gives the power series expansion for QQ sub infinity to the cube, to the cube power. So you can find such kind of proofs in Bruce Burn's textbook. The title is Number Theory in the Spirit of Ramanujan. And I think you can also find the proofs in Wuhan's lecture. So I will not discuss this kind of proofs. Instead, we will use the theory of modular forms to give a proof. So for any positive integer d, Aitken's U operator is defined as follows. Given any formal power series with coefficient Cn, you act with this U operator U sub d. It selects the coefficient. It selects the terms in which n is divisible by d, and then you change the power nd to n. So this is the definition. For example, if you have such kind of sequence, for example, you have such kind of sequence, then you act with U3, then you just pick out the this part, C3n times q to the nth power. And we need a very basic proposition. If Fz is a modular form on the congruent subgroup gamma 0 n with character chi, and d is a factor of n, then after acting with the U operator ud, the function still belongs to the same space. So Fz acting with ud is still a modular form on gamma 0 n with the same weight and the same character. Okay, now we need another key fact. For L being to 5, 7, or 13 being these 3 primes, we denote Z L tau to be the quotient of eta L square tau over eta tau. So in other words, if you don't remember the definition of the dedicated eta function, let me write the original, the easiest way for this definition. This just means 1 minus q to the L square n. L square n divided by 1 minus q to the n. Yeah, this is the function ZL. And there is a very well-known fact says that any modular functions on gamma 0 L can be expressed as a rational function of the so-called hop module YL. So YL is called a hop module, and it is defined by this rational by this quotient of dedicated eta function. So in other words, if you are not familiar with this eta function, it is defined as 1 minus q to the ln minus 1 over 1 minus q to the nth power. Then you have you take a product here, and you have some extra q. You have some extra q. I think it's q here. So this is a function YL, and the fact says that any modular functions on gamma 0 L can be expressed as a rational function of YL. Okay, that's enough for our proof. Now let's prove the modular 5 identity. It is easy to check by some knowledge from modular forms. We can check that eta of 20 factor divided by eta of tau. In other words, it is this kind of infinite product. Or in other words, if you remember that the generating function of Pn Qn is simply 1 over Qq infinity. So you pour this out here, and then 1 over Qq infinity equals to the generating function of Pn. So this becomes this series. And we can prove that L of tau is a modular function on gamma 0, 25. Then after applying the U5 operator, we can prove that L tau acted by U5 is a modular function on gamma 0, 5. So for this, you need some extra knowledge, but this is true. On the right side, if you apply the U5 operator to this product, then the power 25 becomes the power 5, and Pn times q to the m plus 1. For this series, you pick out the P5m plus 4 q times q to the m plus 1 power, because you need the exponent to be divisible by 5. You need this part to be divisible by 5, so you must have 5m plus 4 here. Yeah, you must have 5m plus 4, because 5m plus 4 plus 1 is divisible by 5. So you have this part. And with this fact, now we use the previous slides, the knowledge from the previous slides, which means any modular function on gamma 0, 5 can be expressed as a rational function of the y of the YL. Any modular function can be expressed as YL. Any modular function on gamma 0, 5 can be expressed as a rational function of Y5. So by comparing just very few coefficients, it is easy to deduce that L tau acting with U5 just equals to 5 times Y5. So the rational function is simply a linear polynomial. And this then tells that the generating function for P5m plus 4 equals to this infinite product. So this is our very quick proof for the modular 5 identity. And similarly, we can prove the modular 7 identity. The procedure is very similar. You consider this function L of tau, which is a quotient of eta 49 divided by eta of tau. And by definition, it is also equals to the generating function of Pn times by this infinite product. We can check that this is a modular function on gamma 0, 49. And after applying the U7 operator, we deduce that it is this function is a modular function on gamma 0, 7. Then according to our knowledge, any modular function on gamma 0, 7 can be expressed So it can be expressed as a rational function for y7 of tau. It can be expressed as a rational function in terms of y7 of tau. And by comparing just a few coefficients, you will see that this rational function is indeed a polynomial. It is a quadratic polynomial. So comparing just a few coefficients, we deduce that this function actually equals to 7 times y7 plus 14 times the second identity of Ramanujan. Okay, this is the modular for these two identities. And now let's go ahead. Ramanujan, besides these three beautiful congruences, Ramanujan actually found some deeper congruences. We need flow of x to denote the integer part of x. And for the primes 5, 7, and 11, we use delta LK to be the reciprocal of 24 modulo L to the case power. That is, delta LK is the smallest non-negative integer x, satisfying that 24 times x is congruent to 1 modulo L to the case power. And Ramanujan generalized the previous congruences. He discovered the following three sets of congruences. That is, for any positive integer k, p5 to the case power times n plus some delta is always divisible by 5 to the case power, and similar for the modular powers of 7 and modular powers of 11. And in particular, when k equals 1, this reduces to the original congruences. So these congruences is also discussed by Wuha's lecture. So I'm just reviewing these facts. And Watson gave a proof for the first two congruences. This was proved by Watson. Although Ramanujan also outlined a proof for these congruences. And after about 30 years, Aitken gave a proof for the third one, for the modular powers of 11 congruence. And of course, Herschel and Hunt gave an elementary proof for the first one. This is elementary proof was given by Herschel and Hunt, and the elementary proof for the second one was given by Frank Garvin. And when k equals to 1, this reduces to the original congruences. Now let's review some other facts from Wuha's lecture. This actually says that the number of partitions of 5n plus 4 is always divisible by 5. How can you explain this from the combinatorial aspect? So in order to explain the above congruences through a combinatorial perspective, Freeman Dyson introduced the concepts of rank and crank. So he defined the rank of a partition as its largest part minus the number of parts. And we use capital N Mn to denote the number of partitions of n with rank m. Then we use capital N A, capital M n to be the number of partitions of n with rank congruent to A modular m. So these are several counting functions here. Then Dyson conjectured that the sets of partitions of 5n plus 4 can be classified into 5 equinumerous classes of partitions. That is, according to the residue of their rank modular 5, Dyson's conjecture that the number of partitions of 5n plus 4 with rank congruent to 5 modular 0 is equal to the number of partitions of 5n plus 4 with rank congruent to 5 modular 1 or modular 2 or modular 3 or modular 4. So this means that 5n plus 4, the number of the partitions of 5n plus 4 can be divided into 5 equinumerous classes. And then this naturally explains that y5 p5m plus 4 is always a multiple of 5. And this also similar things works for p7m plus 4, 7 plus 5. But this conjecture was only confirmed 10 years later by Aitken and Swenater by studying the generating function of this rank counting function. And the rank successfully explains Ramanujan's congruences modulo 5 and 7. However, it does not explain the partition congruence modulo 11. And Dyson guesses that there exists another partition statistic called crank that can explain the third congruence. And the definition of crank was only later given by Gowan and given by Andrews and Gowan. And similar to the notion of rank, we use capital M of Mn to be the number of partitions of n with rank M. And we use capital Ma, capital M and n to be the number of partitions of n with rank congruent to A modular capital M. So these are two counting functions with respect to crank. And Dyson conjectures that by classifying the partitions of 11n plus 6 according to the residue of the residue of the crank modulo 11, then the partitions of 11n plus 6 can be divided into 11 equinumerous classes. So this naturally explains that P11n plus 6 is a multiple of 11. And this was later confirmed by Andrews and Gowan. They gave the explicit definition of crank. Okay, so what can we do after all these works? Around 2003, Aitken and Gowan studied the moments of ranks and cranks. So for a non-negative integer j, they defined capital Nj of n to be the jth moment of the rank function. That is, it is a summation of capital Nk of n times k to the jth power. Here k is over all integers, but this is actually a finite sum because we have the fact, we have a simple fact nkn equals to 0 when k is greater than n, or when the absolute value of k is greater than n. So this is actually a finite sum. It is not it's a finite sum. So there's no need to worry about the convergence because it is actually a finite sum. And similarly, we use capital Mj of n to denote the jth power of the crank function. Then a simple fact is that since the rank function is an even function with respect to k, and also the crank function is also an even function with respect to k, this means all the odd order moments of ranks or cranks are 0 because when j is even, when j is odd, then you can easily prove that njn equals to 0, and the capital Mjn is also equals to 0. You just use this fact and grouping the k to the j. The reason is k to the j plus negative k to the j equals to 0. So this means these two facts. And hence, we only need to consider the even order moments. The even order moments are positive numbers, and they have really nice arithmetic properties. First, for the zeroth order, n0n and m0n are just the same with the function Pn. And for the second order, Dyson proves that m sub 2 of n equals to Pn multiplied by 2n. So it differs from Pn only by a simple factor. So what happens for the next? Aitken and Gowan proved that for k equals to 2, 3, 4, and 5, there are polynomials alpha k and beta kj, such that the two case rank moments can be expressed as a combination of n0 of the second moment and the 2j's moment of the crank, and the coefficients of these combinations are some polynomials in N. These are some polynomials. Then next, and around 2007, George Andrews introduced the case symmetrized moment function. In the original definition, if you still remember, in the original definition, it is defined in this way. It is defined by m to the case power times capital N m of n. But now, Andrews replace this part by the binomial coefficient, by this part. Then again, since capital N is an even function with respect to m, so we still have we can still prove that the odd order moments are all zero. And from the expansion of the binomial coefficients, we can easily see that eta 2k of n can be expressed as a linear sum in n2j n and vice versa. So by studying eta 2k of n, you will know the properties of n2j of n. And by studying n2j of n, you can also know the properties of eta 2k of n. So in fact, they are equivalent. You can study just one of them. And Andrews proved that, found the generating function for eta 2k of n. He found that the generating function can be written in this way. So Andrews also obtained some nice congruencies for the rank moments. For example, he proved that n2 of 5n plus 1 and n2 of 5n plus 4 are all divisible by 5. This also holds for the second symmetrized moment of the rank function. So eta means the symmetrized moment, n is the original moment. And there are also some congruencies modulo 7. And in 2011, Gavin defined the case symmetrized moment of cranks by the notation is mu k of n. So in the original definition, in the IIP and Gavin's original definition, the case moment of crank is defined by this way: m to the case power times capital M mn. And he also replaced this part by this binomial coefficient. Then again, we can prove that all the odd order symmetrized moments are zero. Hence, we only need to consider the case when k is even. And many of Andrews' results for eta k of n can be analogously expanded to mu k of n. For example, Gavin found the generating function for mu k of n. This formula is very similar to the previous formula for eta 2k of n. And from the above works, we see that the moments of ranks and cranks actually have very rich combinatorial and arithmetic properties. Breman showed that given any prime L greater than 3 and fixing some integers k and j, there are infinitely many arithmetic progressions am plus b such that eta 2k of am plus b is divisible by L to the jth power. So there are some similar results for the partition function p of n. So this is an analogous result to the partition functions. And Andrews also proves that asked the reader to prove that eta 4 of 25n plus 24 is divisible by 5. And this was the proof is actually easy. This was given by Gavin in his review for Andrews' paper. And Gavin also found the new congruencies such as eta 6 of 40n plus r is divisible by 7 for 4 different values of r. So we have a congruence modulo 5, have congruence modulo 7, and the order range changes from 4 to 6. So natural question arises here. Do the rank and the crank moments satisfy congruencies modulo arbitrary powers of primes like those of P of n? Because for P of n, if you remember, we have P5n plus j, 5 to the jth power. yeah, we have such kind of congruencies modular 5 to the j power. This holds for any j greater than or equal to 1. So we want to know whether the rank and moment have similar congruencies modular arbitrary powers. And the answer is yes. So in order to study the moments of rank and crank, we first represent them using Fourier coefficients of some spatial weakly holomorphic modular forms. Okay, recall the delicate eta function we defined in our first part, which is defined in this way. And then we recall the sum of divisor function sigma m of n, and then recall the Bernoulli number. We recall the weight 2R Eisenstein series we have defined in the first part. This is the Eisenstein series. And now we define the sequence E2R of m by the quotient of E2R tau divided by QQ infinity. And when you make a Fourier expansion for this function, we denote the nth coefficient by E2R of m. And for convenience, we denote E0 as we define E0 to be the function 1, so that Pn, the partition function Pn just equals to E0 of n. So this function can be regarded as an extension for the partition function, because when you change r, you will get some other integer sequences. And by using the theory of quasi-modular forms, we can express the case correct moments and the case rank moments in terms of E2R of n and some other suitable functions. So for example, we prove that the fourth correct moment can be expressed as a linear combination of E4n, the partition function Pn, and n times Pn, and n squared times Pn. And similarly, the sixth moment of crank can be expressed as a linear combination of E6, E4, n times E4, Pn, n times Pn, and n squared, n cubed times Pn. So since the properties of Pn is well known, in order to study the properties of M4 and M6, it suffices to study the properties of E4, E6, and more generally, it suffices to study the sequence E2R of n. And hence, we will now focus on E2R of n. Now we want to discuss some general congruencies for E2R of n. First, by following the method used by Algrim, Breeman, and Aujue, by using the action of Heck operators, we obtain the following general congruencies. This is based on our joint work with Professor Yang Yifan, who is my collaborator. And the paper is published in the Journal of Number Theory in 2022. The first result is for r, it belongs to equals to 2, 3, 4, 5, or 7, and any positive integer m and any prime greater than or equal to 5, and any integer n, we have such kind of congruencies. So this congruence is modular arbitrary powers of L. And in addition to this result, for some small values of m, we have some supplementary results. This is summarized in theorem 3. For the same set of values of r, and for any m and any prime L, so this is the Jacobi symbol. When the Jacobi symbol equals to 1, we have these two congruencies, and when L does not divide m, we have the following congruence relations. Yeah, now let's turn to the generating functions to turn to another method. As we have seen in studying the one of the methods to prove such kind of congruencies is to find the generating function for the substances. So we give a way to represent the generating function for E2R of n on such kind of arithmetic progressions. And in particular, this procedure applies well to the case r equals to 0. If you remember, E0n is the same with Pn. So this also gives representations for the generated function for the Pn. Oh, okay, let's see what we have done. This part will be, the notations here will be relatively complicated. If you find this boring, you can just take a rest. So first we use L2, L sub 2R, L0, or you can just regard this as L2R 0 to be very 2R Eisenstein series. Then we for I greater than or equal to 1, we recursively define these two, we define the next function. L2R minus 1 is the same as L2R minus 2 times ZL. ZL, you may have already forgotten what is ZL. ZL is L eta L square of tau divided by eta of tau. So multiplying by ZL, then we acting with the U operator UL, we define this as the 2R minus 1's function. And when you define the L2R minus 1, then you're applying the U operator once more, you get the function L2I. So this was defined recursively. And next, by induction on I, it is not difficult to see that L2I minus 1 actually equals this infinite product times the derivative function of E2R on this arithmetic progression, and the L2I equals this product times this derivative function of this subsequence. So these two subsequences are what we really need. So we will try to give expressions for L2I minus 1 and L2I. And for that, we need another proposition. For these three spatial primes and any positive integer r greater than 2, we prove that there exist polynomials px and qx such that the quotient of E2R L ter over E2R of ter can be written as a rational polynomial. We have the polynomial p in the denominator, we have the polynomial q. And we can also evaluate the degrees of these two polynomials. Okay, all these things are not important. You don't need to go through all the details. You just need to know we have such kind of equalities here. And in the next, we will write this as E2R tau divided by p equals to E2R of tau divided by q. So this means we have such kind of equality. And now we denoted by this quotient as another new symbol. We denoted by E delta to be the quotient of this E divided by Q. So this is denoted by E delta. And in particular, when r equals 0, E delta 0 is defined as the function 1. And we can show that there exist some integer sequences Mij such that when you multiply by E sub 2r, E delta sub 2r by the s power of ZL, then you act with UL. We can express it as the product of E delta 2r times the times of polynomial in YL. Okay, just forget this. This is the details is not is very tedious, and I hope you can focus on the main ideas. So with this said, we can actually prove the following theorem. We find that there exist integers a, k, j such that the case generating function L sub k can be written as E delta 2r times the polynomial in YL. And also for the coefficients a, k, j, we can find their recurrence relations. So this means all these coefficients can be explicitly calculated. So we know all these coefficients. And then in order to study the congruencies, we just need to analyze the analytic properties of these coefficients. And for these three spatial primes, we can use our previous theorem to give generating functions. And then we can establish congruencies by analyzing these representations. And for the spatial plane L equals to 11, the things becomes more complicated. We need to use another method of IT and Golden, and I will not discuss this. So after going all these messy calculations, we actually have some very nice. Since the procedure applies well to any R, we will use R equals to 2 and 3 as examples. So now I will show you what we have obtained by using this kind of techniques. So for the first, for R equals to 2, which means we are considering E2Rn, the properties of E2Rn. When R equals to 2 or 3, we are actually considering E4 and E6. So for E4, we prove this set of congruencies modular arbitrary powers of 5, 7, 11, and 13. So we have this kind of congruencies. And similarly, for R equals to 2, for the E6, we have similar congruencies modular arbitrary powers of 5, 7, 11, and 13. So this is a bit surprising because for the partition function Pn, we only have congruencies modular powers 5, 7, and 11. For 13, we only have congruence recurrence relations, but not as simple as this, as I show as these congruencies. And then after knowing the properties of E2R of n, we can use them to study the properties of the rank and crank moments. So by using the theory of modular forms, as we mentioned before, all the rank and crank moments can be expressed as linear combinations of the function E2R of n and the polynomials of n times P of n. So since now Pn is clear, we know the properties of Pn, and we know the properties of E4n. So you also know the properties of n2n. Then you can use all this information to get properties of n4n and n6 of n, of course, also for m4n and m6 of n. So similar formulas for other cases also exist. And with all these results, the above formulas allow us to derive congruencies for the fourth and sixth and all other order moments for rank and cranks. For example, for the fourth moment of ranks, we prove that M4 is M4 satisfies this kind of congruencies modular 5 to the k minus 1's power, and M4 satisfies congruence modular powers of 7 and 11. So this is very similar to the partition congruencies for P of n. And similarly, we have theorem 8, which gives similar congruencies for M6. So this is for the crank. Is for the crank moment. So M is here is for the crank moment. And next for the for the mu sub 2k of n, this was defined by Gavin. And if you still remember, this was defined by Gavin. We also know that mu sub 2k of n can be expressed as linear sum of m2i of n. So for example, mu 4 of n can be expressed as m4n minus m2n. And with since the properties, since m4n and m2n can also be expressed by E2R of n and P of n, we can express these functions by something we know, such as E4, E6, Pn. And since the right side is clear to us, the left side is also clear to us. So combining all this information, we find the following congruencies modular powers of 5, 7, and 11 for mu4 and mu6. Okay, similarly, for the moments of ranks, we can do some similar thing. We find that the fourth moment of ranks satisfies congruencies modular powers of 5 and powers of 7. And similar for the sixth moment of ranks, we also have congruencies, such kind of congruencies. Okay, for Andrews, for the symmetrized moment of ranks, this was defined by Andrews, if you still remember. We can also express eta 4 and eta 6 by linear combinations of something we know, and then we can get congruencies for eta 4 and eta 6. So these are the congruencies modular powers of 5 and 7. Okay, the last part, we can also apply our results to some higher order SPT functions. So what is SPT function? Recall that ITK and govern, they did not give the relation between N2N and M2N. This missing relation was later found by Andrews through the study of the smallest part function. So what is the smallest part function? The SPT of N counts the total number of appearances of the smallest part in all partitions of N. So the smallest part, this is the reason for using SPT. So we use SPTN to count the total number of appearances of the smallest part in all partitions of N. And Andrews discovered that SPT of N equals to NPN minus 1/2 of N2N. So in other words, since Dyson proved that M to N equals 2NPN, so this yields that SPTN equals to 1/2 of this difference. And this can be regarded as the relation between M2 and N2. Okay, now let's continue. Since SPT of N can be expressed as in terms of M2 and N2, govern and also SPTN satisfies some very nice congruencies. Andrews proved that SPT 5n plus 4, 7n plus 5, and 30n plus 6 is divisible by 5, 7, and 13 respectively. So for more detailed introduction, you can read the survey of William Chen. And motivated by the relation, Garvin defines the higher order SPT function SPTKN to be the difference of mu2k minus eta 2k. Now, since we have already known the properties of mu2k and eta 2k, we can get congruencies for SPTKN as some byproducts. Okay, and SPTKN also have some nice combinatorial interpretations. So for SPT2 as an SPT3, Garvin provided some congruencies modular simple powers such as modular 5 and 7. They have he found such kind of congruencies. So according to our previous results, since we know congruencies for mu and we know congruencies for eta, so naturally we know congruencies for SPTKN, and this yields the following results. We find that SPT2 and SPT3 satisfies such kind of congruencies modular arbitrary powers of 5 and 7. And this is the end of my lecture. Thank you very much for your attention.
Give applause to him. Wow. Okay, thank you very much. Maybe any question? No? Yeah, because some of you are new in integer partitions, and especially for modular forms. Basically, in 2020, we also have a SIIMath school related to representation theory, and one of the topics also cover modular form. So you can find in the internet from Google, SIIMath school 2020 UGM. Then one of the top there also about modular forms. But yeah, I'm really happy to listen Dr. Wang's talk, because there are some parts that I would like to say, I want to mention as covered by him. So yeah, thank you very much for completing the materials also, not only about your research, but also a lot of parts how to apply modular form in partition theory. But I'm still curious about the SPT function. Are you here? Yeah. Can you hear me?
Yes.
Yes. Okay. So I'm still curious because for the SPT function that consists of two parts, right? The mu parts and the eta parts. And how Garvin get the idea to make the combinatorial interpretation, because when we have the summation and then it is divisible by 5, it doesn't mean that the first part is divisible by 5 and the second part divisible by 5.
So you are asking the question giving combinatorial explanation for this congruence?
Yeah.
Actually, I am not very familiar with the combinatorial interpretation to this congruence, but I think there are some works there. So they can use something like a vector rank or vector crank to explain such kind of congruences.
Okay.
Yeah. Maybe you need to check the reference. I think there are some explanations here.
Yeah.
But I don't know the details.
Okay. Yeah, thank you very much. Maybe another question? No one? Because modular form is very useful in partition theory. That's why some of you asked me. So when we learn about integer partition, so we have to be strong at generating function. Not only generating function, a lot of things. Because we also learn about algebra. If you talk about the modular forms, basically it is a group. So you still have to know about the group parts and also some complex analysis. That's of course, especially for functional analysis, and that's very useful. And this part is, I think that's really deep. So, thank you very much.
Thank you.
At least we know the idea how to apply the modular form in partition theory. Because this morning I mentioned to them, it looks like the congruences looks like simple, like SPT 5n plus 4 congruent to 0 modulo 5. But the proof behind it, that's a different thing. So maybe once more, let's give him a big applause.